Good morning and good afternoon, scholars. Welcome back to geometry class. This is going to be our last video of the year. Today we're going to go ahead and answer some of your questions about the finals, going over various questions that we got set up here. Going to pick and choose through that notes packet that was posted up on Google Classroom for you. Just as a last reminder, please hand in some of your late work. I'll be more than happy to grade your missing work. Just please email me first if you're going to email me after you complete something, post it up on Juno Pods or Google Classroom. Just let me know that you finished it. But without further ado, let's get through our packet for today. What I'm going to be showing you here is basically I'm picking and choosing certain types of questions that I feel like are possibly going to be coming up on your exam. Just as a reminder, our main focus of our class is to get this notion, this idea of why these properties work, and the way that we express them is going to be through algebra questions, multiple choice questions about context, but as always, my main takeaway for you guys is understand why these properties work. First thing that we're going to do for today is look on page 2, question number 5. Page 2, question number 5, we're asked, which of the following statements about parallelograms is always true? If we get a question like this, whether that be like history or science class, if you want to have some list off things that are proof questions, just go through your mind, go through that little catalog you got going on, and just try and write down as much as you can, possibly before going through the question, if you want to set yourself up for best success. But as always, if you're going through and you know this stuff by heart, you can read through the questions, but make sure you get through all the presented options first in case there's some type of intentional confusion or misleading there. If we look at our options for parallelograms, we're told that our diagonals are congruent. That's not true. That's only for objects which have 4 90-degree angles, like our square and our rectangles. They have those nice congruent diagonals. Diagonals bisect each other. That is definitely true. That's for all parallelograms. They hit each other at their respective midpoints. Diagonals are perpendicular. That's not true. That's dictated by the congruent sides, all 4 sides being congruent, so our squares and our rhombuses. Here, let's see. And our last option, diagonals bisect their respective angles, and that one's not true. That's going to be, once again, with our squares are rhombuses. So with question number 5, our first answer for all parallelograms is that their diagonals bisect. And that's going to be option 2. So if we look at our question here, we're told that in parallelogram HAND, says below is drawn diagonals HN and AD intersecting at S. Our question is, which of these statements is always true? What we just saw in our previous question 2, column 5, is that our diagonals always bisect one another. That doesn't mean all of our portions that get broken up are going to be congruent to one another, but at least in this particular example, DS is going to be congruent to SA, HS congruent to SN, and vice versa. So if we look at the question here, we're told which of these statements is always going to be true. For this particular one, we have AS is equal to half the length of the diagonal AD. If our diagonals bisect one another, we know that those pieces or segments that accumulate, that add up together to be our diagonal, are going to be half the length of the whole diagonal. They are bisected. Those are the bisected pieces. So for this one, we can go ahead and say 2 once again. But let's continue to go through some of the questions here. What we're going to do is take a look at page 3, question number 9. Along the bottom here on this page, we're talking about our geometric mean theorem. That's once again when we're able to essentially take apart triangles because we know that they have 3 congruent angles, all in the same orientation. We can pull these triangles apart, match the corresponding sides, and set up those equivalency statements. In these particular ones that we did in our class, we used this notion of the boomerang theory and our heartbeat method to go about solving for values. In question number 9, if we wanted to solve for z, we would use that heartbeat method, where we do a statement of 9 over 6 and 6 over z. 9 over 6 equal to, coming back down, 6 over the letter z. From here, we essentially just go ahead and cross multiply everything out. 6 times 6 is 36 equal to 9z. We then go ahead and divide by 9. We end up getting a value of 4 for letter z. If we now want to go ahead and solve for our missing value of y over on the right hand side here, we're going to use that boomerang method where we do 9 plus 4 or 13 over y, coming back down around over our now known value of 4. If we set up a cross multiplying system here, 13 times 4 gives us a value of 52 equal to y squared. Square root of 52 breaks down and gives us a value of about 7.2 equal to y. If we wanted to go ahead and do this, same thing for x, we're going to set up another boomerang method value going around the left-hand side of our figure of 13, or 9 plus 4, over x over 9. Set up our cross-multiplying statement and solve for our missing value. We're looking at page 4 now. On page 4, we are presented with a nice detailed setup about transformations. The transformations I would like for us to go over, wink wink, is going to be our rotation. You'll see along the center of the page we have a diagram that gets set up, tells us all about rotations. Rotations is a type of one of multiple types of transformations. And when we describe this idea of transformations, we're talking about ways that we can move an object around our coordinate plane. In some cases, we maintain what we would say is congruency, in that all we're doing is saying reflecting or rotating or sliding an object over. That figure, that point, still has the same size, still the same area, perimeter, and all that. All we did is articulate it in a way. All we did was rotate that box. The box is still the same size. Everything is kind of in the same orientation, but it's been altered. It's been transformed. If we're talking about rotations, we're talking about an object where we take it and move it. When we're referring to the degree measure, our degree measure is associated with that counterclockwise direction. So if we rotate an object around 90 degrees, 180, 270, and 360, we're going to be going in the counterclockwise direction. So based upon our example that's in our work packet where we have the triangle ABC, we're going to be rotating it 90 degrees. We're going to go from the first coordinate plane over to the second. When we do that, we have a system of equations that we can use. Whenever we're referencing a rotation around the origin, or say point 0, 0, we're just going to use this quick methodology here. All we want to do is, if we want to rotate a point, we use this little formula where we're going to be swapping our values, say -4, comma 2, -2, -4, and +4, comma -2. This allows us to take that figure and rotate it around in our coordinate plane itself. Nice quick formula. Okay, let's continue on with our next question here. Our next question, we're going to go to page 5. Question number 1 on the left-hand side. with these sorts of questions, we're being asked to find the volume of the figure here. When we're thinking about volume, thinking about these equations, it's based on this notion of a base or a cross-section within our figure. Cross-section is essentially if we took this object here, samurai sword it, cut it in half just like our orange, what area does that figure represent, that layer that's been produced? In objects like cylinders and objects like prisms, we know that as long as we're cutting parallel with our base, that cross-section that's developed is continuously the same size. And that continuous cross-section allows us to find our volume by doing our base times our height. And always remember, in our study guide, I have links to our previous videos where we go over all this in really super strong detail. Our question here, we're going to have to locate our base in our cylinder. Our base is going to be our circle along the bottom, and our base equation is represented by the two-dimensional form. In a cylinder, the two-dimensional form or two-dimensional figure on the bottom is going to be a circle. Our circle equation for area, our 2D version, is going to be pi r squared times our height. In this particular example, we have a radius of 8, so we're looking at 8 squared pi times our height of 7. If we go ahead and multiply everything out from here, we have 64 times pi times 7. Next, what we're going to go ahead and do, combine all of our values here, and we have 448 pi. So if we go ahead now and we look at on the right-hand side of our page, page number 5, question number 1, we have another question here similar to volume. Again, here in this example, we have a cone drawn along the bottom. In comparison to our cylinder, we do not have this notion of a constant cross-section, where if we cut into the figure, we have a consistent shape. What we end up having to do is, as opposed to using this equation of volume equals base times height, for our cone, we're going to add in this notion of times 1/3, where we can calculate for this depreciating value as we go up to the top. Go ahead and set up our equation. Our base is going to be it's going to be pi r squared, or 2 squared pi, times our height of 7 times 1/3 for that depreciating value. If we go ahead, we have 4 times 7, or 14 pi times 1/3. Go ahead and solve. We get a value. If we divide 14 by 1/3, we get 4.6 pi is equal to our final volume. We're going to go ahead and write our notes as well. To be specific, we're going to have 4.6 kilometers cubed. What I'd like to do now is take a look at our next page. Next page has got, we're going to look at question 18 on page 6. This one here, we're looking at our triangular sum theorem. Our triangular sum theorem is basically this notion where the measure of all the angles inside of a triangle is equivalent to 180 degrees. Therefore, if we want to go ahead and solve for our missing angles, we're going to set everything up nice and equivalent to 180 degrees. So for here, we're going to do 8x plus 2 plus 70 plus 60 equal to 180. This value right here is going to be equivalent to 130 plus 2. We have x plus 132 equals 180. So the first thing we always want to do is combine all our like terms, and then go ahead and solve for x. So we have 48 equal to 8x, divide out our 8, and we have a remainder of 7 equal to x. Here we have our next question along the bottom. We're taking a look at page number 6, question number 8, and this works off this notion of the exterior angle theorem. This concept describes that the exterior angle formed by a point connected to a triangle is going to be equivalent to the other two angles. If we think about the way that we would go ahead and solve for angle RPQ, this inside portion here, we would go ahead and say like 180 minus 35 minus 95 gives us x, or that 180 minus x gives us the value of these two other angles. We can say the same thing, that 180 minus x gives us the value of this missing angle, which is equivalent to these two ones right here. So pretty cool. If we're going to set up an equation to solve for these two, we're going to do 35 plus 95 is equal to our question mark angle, or just simply 130 degrees is equal to our question mark. If we want to go ahead and solve for a missing angle, what number plus 130 gives us 180, and that's going to be 50 degrees as well. Last but not least, we are going to go ahead and take a look at page number 10. We're looking at that option for sine, cosine, tangent. If we think back about a month or so when we covered this material, sine, cosine, tangent allows us to identify the lengths of missing sides or angles within a triangle when we work with a 90-degree angle. There are other ways to use sine and cosine to figure out missing portions when we're not using 90, but for the course context of our class, we're using it with right triangles. If we take a look here, in this particular example, we have some data already filled out. We're told we have an angle of 90 for M, an angle of 36 for N, and if we go up to the top here and look at angle P, we know that we can also solve it by using that angle sum theorem once again. For angle P, we can just quickly go ahead and say that this is 54 degrees as well. If we want to go ahead and identify one of our missing sides here, we have to go ahead and do this notion of labeling the adjacent, hypotenuse, and opposite side when we set up our systems of SOHCAHTOA. Angle PM would be considered our opposite side, because if that's our theta or our reference point, it's all the way on the opposite side of the triangle would be that missing side. If we have a known theta angle in opposite side and what we would call our adjacent side, we would go ahead, opposite adjacent, and we would use the tangent system to solve for PM. So we can say that tan 36 is equal to opposite over adjacent, our unknown opposite over our adjacent of 28. We go ahead in our calculator and start to cross multiply. Tan 36 times 28 gives us a value of 20.3. If we're going to use our calculator, once again, this is always dependent upon specific unit you're using, but if I do 3610, multiply it by 28, I get about 2.3 equal to side PM. If I now wanted to go ahead and solve for my last side, side Pn in this right triangle, I can go ahead and say, oh, Pythagorean theorem, a squared plus b squared equals my hypotenuse of c squared. Or I find it a little bit easier, since we are already using sine, cosine, tangent, that we can just use adjacent over a hypotenuse or a cosine value, cos 36, to solve for that unknown hypotenuse value. Go ahead and calculate everything out. We'll have cos 36x is equal to 28, or value of 34, equal to Pn. So these are just some of the examples from the finals packet that you'll have responsible to hand in today. As a reminder, what is due or was due this morning was having at least 2 questions answered from each individual page. In our class today, we're going to go over some of the other questions that are there. Please come today, this afternoon, for our live classes. Be more than happy to help answer kind of any questions that you have from this particular packet. I'll have some already pre-answered that we'll go through, but of course, if you have a particular one you want to focus on, then we'll focus on those as well. Separately from that, next week you should receive another video just like summarizing expectations for the final, just to go over some stuff with you, but no additional work. This is going to be the last really assignment that you have from our class. So with that, hope you're having a nice time at home, the best that you can. Stay safe, wash your hands, stay inside the best that you can. If you have any questions about the final, please reach out. I'll be more than happy to help answer anything for you. All right, so bye everyone.